Okay, the next two problems now we'll do. The next problem, again, this is not part of exam 1 from 2018, but a new problem. And it's very similar in this case to problem number 5, I think, if I remember right, from exam 1. It's a problem about the interaction between a cluster of 4 argon atoms, only this time the interaction is due to induced dipole interactions, or in other words, Leonard-Jones interactions. It says that the cluster of atoms forms a regular tetrahedron, which means something that looks like this. Actually, let me put the picture down here from the key. 4 atoms at the corners of a regular tetrahedron, and that means that the distances between all 4 different atoms is equal to 3.4 angstroms. So it says here that the Leonard-Jones distance is 3.4 angstroms, and the spacing between the atoms is 3.4 angstroms. That means that the interaction energy for any one pair is equal to minus the well depth times the natural interaction energy, or the Leonard-Jones distance, divided by r to the 12th power, minus 2 times big R over r to the 6th power for one pair again. We have in this case a total of 6 different pairs. Right? There's 4 atoms, and anyway, 6 for any 4 particles, there's always 6 pairs, 6 possible pairs. In this case, they all have the same distance, so the energy is going to be minus epsilon times 6 times all this other stuff. We're also saying that the distance between all the atoms, this r, is the same as the Leonard-Jones distance. This is the Leonard-Jones potential. The Leonard-Jones distance is the big R, so that means that this big R over little r is just a 1, and that's raised to the 12th power, but it's still a 1, so it's minus epsilon times 1, minus, actually this should be a plus here, to the 12th. Same here, 2 times 1 to the 6th. That's just 1 minus 2, which is minus 1, and so we get minus 6 times the Leonard-Jones well depth. It says that the well depth is 1 kilojoule per mole, so it's minus 6 kilojoules per mole of interaction energy between all 4 of these clustered argon atoms. In the earlier problem, we then calculated what the probability is of seeing a cluster like this versus seeing the same 4 atoms separated to infinity. This problem doesn't ask for that, so we're done now. Problem number 8. 1 mole of liquid water is contained in a piston in the presence of temperature and pressure baths. So we have something like this. It's always good to draw a picture. 1 mole of water, liquid water, in a piston in a cylinder with a piston, and there's a T bath and a P bath out here holding the temperature and pressure constant. It says that this is going to go through a process, and for each step in the process, say whether the step is reversible or irreversible. So here's a situation where it doesn't tell you whether it's reversible or irreversible. You have to decide for yourself. And then calculate all these quantities, the heat, the work, the change in energy, the change in enthalpy, and the change in entropy. And then do the same thing for the overall changes in heat, work, energy, enthalpy, and entropy for not just for every step, but for the overall process. So what is the process? Here it is. First of all, we start at temperature of 298 K, right, 25 degrees C, and we warm the system up, and there will be a small thermal expansion during that, but it doesn't change to 373 K, but at a constant pressure of 1 atmosphere. but no vaporization. The water just warms up to, we know this is the boiling point, right? This is 100 degrees C, so it's on the verge of boiling, but it remains as liquid water. Then we put in some more heat, right? In order to actually vaporize this water, even if it's at the boiling point, we have to put in some more heat. So we put in some more heat and boil all this stuff. Now it's vapor, but we do that at a constant temperature and a constant pressure, so it's still 1 atmosphere out here. The temperature is still 373 K, but we've gone from liquid water to vapor. And then the third step in the process is we slowly lower the pressure outside to not 2 atmospheres, 1/2 atmosphere. And of course, in the process of that, since the temperature hasn't changed, the gas must expand. It also says that the water vapor can be treated as an ideal gas. That's not the greatest approximation in this case because this water vapor is right at its boiling point. Interaction energies will be, or interactions between the atoms won't be completely negligible in this case. We should really use a better equation of state if we wanted to do this accurately. But since we don't want to spend all day doing things really accurately, we'll just make the approximation that it behaves like an ideal gas, and that'll be good enough. All right, so this is our overall process, 3 steps. And we want to calculate all these quantities. We want to calculate Q, W, delta U, delta H, and delta S for every step, and then also overall. So this is going to take some time. I might only just do 1 problem this time rather than doing 2. All right, so for the first step, let's call this 1, this 2, this 3. For step 1, we're just warming something at constant pressure from 298 to 373. And notice it's doing it, it doesn't actually say, does it? So maybe it isn't the best wording. Let me see what it says. The bath temperature slowly increases. So the bath temperature slowly increases from 25 degrees C to 100 degrees C at constant pressure. So it does say that the temperature of the bath is actually rising. And that means that the temperature outside always matches with the temperature inside. The pressure outside is always going to match with the pressure in the system itself too, because there's a movable piston present and the outside is a pressure bath, and that's not changing anyway. So this should be a reversible process. The forces are always balanced at every point, the forces being pressure and temperature in this case. And so we're doing a reversible warming process, and we want to calculate W for that. For a liquid, I'm going to assume that there's no appreciable volume change, and so the work is going to be equal to 0, no volume change. The heat will be equal to the heat capacity at constant pressure times the change in temperature. We can look up the heat capacity at constant pressure. It's down here at the end of the exam. Where is it? There it is. You can see there's a whole bunch of numbers here for water, and we're going to need some of these other numbers too before long. We want the molar heat capacity at constant pressure for liquid water. That's the quantity we want right there, 75.29. Notice what would happen if we'd used the constant volume heat capacity for liquid water. It would have been 74.53. You can see they're almost the same. I just point that out because I've been saying all along that for a liquid, CP and CV are almost the same, and now you can see that that's actually true. All right, going back then, we have that Q is equal to 75.29 joules per K per mole. We have 1 mole, right? So that's the heat capacity. Times the temperature change. We're going from 298 to 373. That's a temperature change of plus 75 degrees. And so the overall heat change is 75.29 times 75, which is equal to 5646.8 joules. All right, that's heat and Q for the first step. Delta U will be equal to Q in this case. Delta H will be equal to Q in this case, right? Also because it's a QP, right? Constant pressure process. What's delta S? Delta S will be equal to Cp, because it's a constant pressure process, log of T2 over T1. That's equal to 75.29 log of 373 over 298, and that is equal to 75.29 log 373 over 298, and that is equal to 16.90 plus 16.90. Positive entropy change. Why? Because we warmed things up. We put energy into the system. All right, that's step number one. Step number two is vaporization, but notice at constant temperature. So it's a constant temperature vaporization. In that case, what's the work? Well, it will be equal to, also at constant pressure, notice. So it's a constant temperature, constant pressure process. So work is equal to minus P times the volume change for the system. What's the volume change? The pressure is 1 atmosphere. What's the volume change? Well, the volume change will be equal to the final volume minus the initial volume. What's the initial volume? Well, we had 1 mole of water. We know that there's about 1 milliliter per gram of water, and that a mole weighs 18 grams of water, so it's about 18 milliliters. Very small. So this is 18 milliliters. The final volume is what? Well, we're going to treat the gas, the vapor, as an ideal gas. So the volume will be equal to nRT divided by P. N is equal to 1. R is equal to 0.08206. We're using the liter atmosphere value for R, times the temperature, which is 373, divided by the pressure, which is 1 atmosphere, and that will give us 0.08206 times 373 divided by 1, which is 30.61 liters for the final volume. So this is 30.61 here. And that means the work will be equal to minus the pressure, which is 1 atmosphere. I'm going to work in atmospheres and liters here because that's going to be convenient, times 30.61 minus, we got to convert this to liters, so that's 0.018 liters. And you can see, right, this is essentially negligible. The volume of the water is always essentially negligible compared to the volume of a gas when you're doing some kind of vaporization process, because the liquid is just so condensed compared to the gas. And that will be equal to, let's do it here. We'll do it properly. I was going to neglect this, but let's just do it properly. So it's 1 times, so it's going to be minus 30.61 minus 0.018, and that is equal to minus 30.59 liter atmospheres of work. Hold on for a second. I have to stop that wind from blowing. All right. 30.5659 liter atmospheres. Let's convert that to joules. It's 101.3 joules per liter atmosphere. And so that work is equal to minus 30.59 times 101.3, which is equal to 3099 really. Minus 3099.0 joules. All right. So that's the work for step 2. The heat for step 2, what's that going to be? What did we do here? Well, we didn't change the temperature, but we did put a whole bunch of heat in order to cause the vaporization. Basically, we put the heat in because the water molecules have strong attractive interactions when they're in the condensed phase, but no interactions at all when they're in the vapor phase. So we put a bunch of heat in there to break all those interactions. How much heat? Well, that's another number from the chart below. That's the heat of vaporization. Where is it here? Enthalpy of vaporization for water at 373 in 1 atmosphere, 40.6 kilojoules per mole. So that's our heat for this step, 40.6 kilojoules. We have 1 mole, so it's just 40.6 kilojoules. Now we need delta U. That is equal to the 40.6 kilojoules minus the 3099. So 40,600 minus 3099, and that is equal to 37,501 joules, or 37.5 kilojoules. Delta H is the heat change, right? This is a constant pressure process, so it's the QP, and that's just our 40.6 kilojoules. So this is our 37.5 kilojoules. And delta S, what is that? Well, this is a constant temperature process, so it's just Q divided by T, which is our 40,600 divided by 373, and that is 108.8 joules per K. All right, so that's step 2. I'm going to need more space now. I think I'm just going to add a page to this thing. I'm going to shrink that down so the page break doesn't split that in half. And then I'm going to add a page, give myself more room. And do step 3 here. Step 3 is just lowering the pressure to 0.5 atmospheres, keeping the temperature constant. And so for step 3, we have the work is going to be equal to pressure is changing, temperature is not changing. We're going to treat it as an ideal gas. So minus nRT log V2 over V1. We could calculate the volumes, but we know the pressures already. It's easier to work with those. And we know that if the temperature is not changing, then V2 over V1 is equal to P1 over P2. So this is the same thing as minus nRT log P1 over P2. We know those pressures, so this is equal to minus 1 times 8.314 times temperature of 373 times log of P1 is 1 atmosphere, P2 is 0.5 atmospheres, and so this whole thing here is just a 2. And that means that the work will be equal to 8.314 times 373 times log 2, which is equal to 2149.5 minus. Is that right? 2149, yeah, 0.5. All right, joules. All right, that's the work for step 3. The heat for step 3, we didn't change the temperature. We didn't put any heat in to cause a vaporization. Therefore, delta U has to be equal to 0, right? We're going to treat this as an ideal gas again. So we're saying delta U is going to be equal to 0. That means heat has to be equal to minus work. So that's 2149.5 joules plus. Delta U then is equal to 0. Delta H is equal to 0. It's an isothermal process for an ideal gas. Delta U and delta H are both 0. Delta S is equal to, it's an isothermal process, it has to be Q over T. And so that's 2149.5 divided by 373, which is equal to 5.76 plus 5.76. Notice that the sign on the entropy change makes sense, right? We expanded the gas. Entropy should go up. We could also have calculated this delta S using nR log V2 over V1, right? That's nR log P1 over P2. And you can see that that's just the heat change here, which is the negative of this, divided by the temperature, so dividing that T out, and would give us the same answer, 5.76. Okay, so either way would work. All right, that's it for the various steps. We've answered the whole question now one step at a time. All that remains is to calculate, if I remember right, the total changes, the overall changes for Q, W, energy, enthalpy, and entropy. So W total, let's do first, is equal to 0 for step 1, minus 3099 for step 2, and minus 2149.5 for step 3. And that is equal to, oops, come back here, minus 3099 minus 2149.5 is minus 5248.5. Quite a bit of work, in fact. And that's because, of course, we started out with essentially 0 volume here, and ended up with quite a lot of volume by the time we were done. 30 liters of volume, actually 60 liters of volume by the time we're done, I think. Q is then equal to, for step 1, it is 5646.8. For step 2, it is 40,600. So that's going to dominate everything. And for step 3, it's 2149.5, and that is going to be 5646.8 plus 4600 plus 2149.5, and that is 48,396.3, 48,396.3 joules. So 48.4 kilojoules. Why so much heat? Well, obviously it's because we vaporized the water vapor in the meantime, right? The heat that got put in by warming the water up first from room temperature to boiling point is significant, but not nearly as big as the heat necessary to actually vaporize the water. And then we got a little bit more heat, even though we didn't raise the temperature, because we expanded the gas out, and we had to pump some heat in as the work was being done and as the gas was expanded in order to keep the total energy 0 and keep the temperature constant at the same time. All right, then delta U will be equal to Q plus W, Or we could add up to the delta U's from above, but let's do it this way. So that's minus 5248.5 plus 48,396.3, and that is equal to 43,147.8. So notice the work caused us to lose a little bit of energy, but the amount of heat that we put in vastly dominates that. So the overall energy change is positive, but notice that most of that energy change is due to the energy with the heat we had to put in to vaporize the water. Delta H is then equal to, let's see, delta H is always a little tricky, and now I'm forgetting how I did this before. Delta H is going to be equal to, well, it's going to be equal to, let's just add them up. That's the easiest way to do it. So delta H is going to be equal to 5646.8 from step 1. Delta H is 40,600 from step 2. That's the vaporization energy, enthalpy. And then delta H is 0 for step 3, and so that is equal to 5646.8 plus 4600, and that is 46,246.8 joules. So again, dominated by that energy for vaporization. And finally, delta S, let's again just add things up. That's the simplest way to go. So 16.9 plus 108.8 plus 5.76. Notice that every single entropy change is positive for this particular process, because in the first case we warmed, in the second case we added a whole bunch of heat in order to vaporize, and in the third case we expanded. So 16.9 plus 108.8 plus 5.76, that is equal to 131.46 joules per K. And that is it for this problem, and we'll stop there and do the next problem.